Hey, so welcome to this review on the basics of derivatives. Now, why are we covering derivatives as part of an AI series? Well, derivatives show up in a very important way in AI and in a lot of other problems, right? And optimization is one of the main reasons where or places where derivatives shows up. So let's get started. Now, the idea here is to, if you don't remember, your high school derivatives class. And the idea here is just to give you a quick overview, not very mathy, but we'll cover whatever is required to help you kind of understand, the machine learning and deep learning sessions we are putting up for you. So let's dive in. Okay, so let's start. Now, you remember what a function is, right? And the idea is you have a function which takes in a parameter or a variable and basically computes some expression or a collection of expressions based on that and returns or maps it to a particular value. So in this case, we're taking a very simple function. It's a quadratic function. F of x is equal to x squared, which means you give it an x and it just squares it for you, right? Okay. So I've plotted this function here, right, from the interval of -5 to 5. So let's just kind of work out some of these values, right? So when x is -4, which is here, f of x is -4 squared, which is -4 times -4, which is 16. Okay. Now x is -2, so we're down here. What happens now? So -2 times -2 is 4. What if when x is 0? When x is 0, 0 squared is 0. Okay. Next, we're coming to this side of the curve. Now x is 2, f of x is 4, right? 2 squared. And so on. So when x is 4, f of x is 16, and you can imagine what's going to happen in between, or if you kind of increase the range of this plot and you see what happens, right? Okay. So you get the basic idea of what this function is. Now, the interesting question here is what happens, or what we are trying to understand is how do we know how this function changes, right, at any given point? So what do I mean by that? Well, okay, let's take this function. Let's take a point f of x is equal to 2. So we know x is equal to 2. We also calculated that f of x is 2 squared, which is 4. Now, this function here, f of x, if I change x a little, I just increase it a little, how does this function change? Does it increase? Does it decrease? Do you know by how much it will increase or decrease per unit change in x? So if I change x by 1 effectively, how much does it change? It's per unit, right? These are questions that a derivative is trying to answer. Why are we trying to answer this question? Well, there are a lot of reasons. If you're trying to solve an optimization problem, you have a number of variables like a deep learning model, right? And you're trying to optimize the weights. You need to know how, when you change a variable, the function that you're trying to optimize, minimize, changes, right? And so here, what happens, right? So what you do is it's a very simple solution, right? What happens when you want to know what happens when it changes? Well, we've got a plot here. We're going to take a small step, right? In this case, to the right. We're going to add a small value h to x and calculate f. Right? We're saying what happens if we change the input, right? X a little. We're going to take f of x plus h. We're going to say x is 2 and h is 0.01, right? Small change. So f of x is 2 plus 0.01 square, which is 4.0401, right? You can, in fact, I'd encourage you to just calculate this. Okay. So we know that x is equal to 2, f of h is 4. When you take a small step to the right, x plus, right? So 2 plus, small step to the right here. Now, this is obviously a lot bigger. I'm showing this because I'm not zooming in, but assume this is a small step and you're seeing a magnified version, right? It's 4.0401. So what do we see? We see, first of all, that when x is increased a little, f of x also increases a little. But how much does it increase? Well, f of x minus h, x plus h minus f of x. We just do the difference. So difference of this minus 4, which we know is that x is equal to 2. And you get 0.0401. So what we get is when x increases 0.01, f of x increases 0.0401. So what we can do is say, okay, So the change in f, which is given here by delta f, right, divided by the change in x, right, is f of x plus h minus f of x by h, right? Because actually it's x plus h minus x, the x and x cancels by h, which we know is 0.0401 by 0.01, which is 4.01. So what we're finding out is per unit change in f, well, f changes 4 per unit change in x. Okay, so that's effectively what we've put, right? 4.01. Now, what we can do is make this h smaller and smaller because we actually want to understand this change exactly at this point, right? Now, we've taken a big step, but we want to get a value that's as precise as possible. So we keep reducing this. So when you say 1e minus 1 is, 1 decimal point. So 0.1, 1e minus 2, 0.01, and so on. As I keep making this h smaller and smaller, I keep making this calculation finer, more precise. You see that the delta f, delta x, which means the change in f, slowly starts becoming closer and closer to 4, right? So you start seeing that this value is converging to 4, right? And if you remember your, and we are going to come to that, but if you just, if you remember your basic derivatives, derivative of x square is 2x, and at 2 times 2 is 4. So it is converging to 4, right? So now what happens if, and by converging, we means it's coming closer and closer in a very systematic way. Now, just a note here, while I get into the derivatives, this approach of using a small step to compute a derivative is called a finite difference method, right? And it's actually used in a lot of computations. So when you're computing numerically, when you don't know an analytic derivative, it's a complex function and you can't get an analytic derivative. This approach is actually used in a lot of simulations and computations, right, to estimate the derivative. But now in this case, it's a theoretical example. So we say we can make this interval infinitesimally small, right? Very, very, very small. When you do that, you get f of x minus x plus h minus f of x by h. But now h is becoming very, very, very small. And now the delta is replaced by df by dx. And so that is the derivative of f with respect to x, right? And so we've kind of got the basic idea of what a derivative is. You keep reducing this interval till it's infinitesimal, right? It's very, 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 very small. And what you get is the derivative because it tells you exact at that instant how much, the function changes by when x is changed or perturbed. And that's called the slope of the function as well. So it's called the slope, which you can imagine at this point, it's just a line that cuts it. That doesn't cut it. In fact, it's just, touching it. And so it's the slope. Okay. Now, the one point, and we're not going to derive this, but for a function to be differentiable, it also has to be continuous. I can add a note on this in the lecture notes in case you're interested. But this is kind of more to get you up to speed with derivatives and not to help you take an exam on it. So we're not going to cover the derivation. Okay, so we've got that. Now, just to give you a little more practice, so we've defined what a derivative is here. We've set up this definition. Can we calculate the derivative for a simple function? We know f of x is x squared. We actually know the derivative, right? It's 2x. So how do we calculate it using that rule? Okay. We're going to say limit h tends to 0, x plus h squared minus x squared by h, right? We've just said that's the derivative. And so x squared plus 2xh plus h squared, a plus b the whole square is a squared plus 2ab plus b squared minus x squared by h. Okay. So x squared and minus x squared go, and we are left with 2xh plus h squared by h. Now we can take an h out here. So it becomes 2x plus h by h times h. And so the h cancels. We're left with limit h tends to 0, 2x plus h. Now we're already saying the limit h tends to 0, and we're looking at a derivative where h is effectively 0, right? So this term is 0, and you're left with 2x, which we know f of x is equal to x squared. The d by dx of x squared is 2x. So we've just quickly derived, what this derivative is, and this will help you out. So in fact, I'd encourage you to go try it out for an x cube, just to give your basic high school maths a little test. Okay, so we've just seen what derivative is. We've done a quick derivation for f of x is equal to x squared. So now let me just give you a little more intuition on this, right? What does the derivative really tell us? So I've plotted the derivative. It's in orange here, and the function is in blue. Now to the right side of zero, what do we see? We see that as x is increasing, so x is going from 0 to 2 to 4, you see that the derivative is positive. It's above 0. We know derivative is the rate of change of the function with respect to x, right? df by dx. So it means that when x increases, the function is also increasing. How about on the other end? Well, here you see as x is increasing, x is going from -4 to -2. What about the value of the function? When x goes from -4, well, the function at -4 is 16, right? It goes to -2. So x is actually increased, right? It's become a less negative number, which means it's increased. The function has actually decreased, right? -2 squared is 4. So the derivative is negative, right? It indicates that the correlation between x and the function is actually negative, meaning as the value of x increases on this side, the derivative, the function actually decreases, right? And vice versa. So it's an inverse relationship on this side, and that's indicated by the negative sign derivative. So hopefully that's not confused you. It's actually giving you a little intuition on how these derivatives work. It indicates how this function is changing. Okay, excellent. So now let's get into some rules. Now, these are all standard rules. So we're not going to derive them, but I'm just going to lay them out. And you'll see some of the important rules, and especially from the context of machine learning or deep learning, kind of keeping these in mind is a good idea, or at least kind of remembering the reference. So we've put these out in the course notes as well. So you can go and check it out there. But for a simple polynomial, d by dx of x to the power of n is n times x to the power of n minus 1. We just saw that right now, right? D by dx of x squared is 2x of x cubed is 3x. For an exponent, it's very interesting. The derivative of e to the power of x is e to the power of x. So, I mean, very simple. For a logarithmic function, d by dx of log x is 1 by x, right? Okay. And then there's the standard trigonometric functions. And for the others, so secant and cosecant and cotangent or cot, you just can use this to derive that. I'm just giving you these. So d by dx of sine x is cos x. Cos x is minus sine x. If tan x is secant square x. And then because we're looking at deep learning, hyperbolic functions actually show up. The tan h function is a very important activation function used in neural networks. So you can see how the derivative of that is there as well. So these are there in the in the notes. So in case you need a reference if you're kind of coming up with activation functions, or you end up using one and need to work out the math, it's a good reference. Okay. Let's also look at some of the basic rules, right? So assume you have two functions, f of x and g of x, both functions of x. Now, if I want to find the derivative of the sum, so I'm adding f of x plus g of x, I want the derivative of the sum. The simple solution is you can take the derivative of each of them. So d by dx of f of x plus g of x is d f of x d of x plus d g of x d of x. And we'll do examples right very, very shortly. You'll actually see how this kind of works in practice. The second rule is the product rule. So you've got two functions, f of x times g of x, and you want to find the derivative of that. Then what do? You say, okay, the rule says that you say d by dx of f of x. So you take the derivative of this and you multiply that by g of x. There's no derivative here. And then you say plus. And then you say you take f of x, there's no derivative there, times the derivative of g with respect to x. Right? So it's again very simple. And then what about the quotient rule, right? So what if you have a function like this? And the answer is you take this, but now you make this a minus sign. So you say df of x, d of x times g of x minus f of x times dg of x by dx. But then you divide the entire thing by g of x squared, which is the denominator here. So the denominator here becomes squared, and then this positive here becomes a negative. Okay. So now that we've looked at some of the theory and understood the basics, let's now do some practical, right? Let's just start differentiating some of these functions and apply some of the rules you've just seen. So you start understanding how a derivative is computed, right? Analytically, that is. Okay, so we've got this function here, x cubed minus 3ax plus 7. So clearly you can already see that it's an x cubed, it's a polynomial. This is by itself is a polynomial. This is a derivative of a polynomial term. So think back, try and remember the rule. When we differentiate this term, you'll see if you remembered it correctly. Then we have this term. Again, you have to, this is a constant, a is a constant. So 3a times x, and what rule do you think we're going to try and apply here? And then you have 7, which is just a constant. Okay, so let's start. So the first rule we apply, well, got a negative and a positive. This is an expression with 3 terms. So we start with sum rule, right? We know that the derivative of a sum of 2 terms or more is basically given by taking the derivative of the individual functions, right? So in this case, you have 3 terms. Same principle, right? The derivative of the sum of the entire thing is equal to the derivative of the sum of the first term, so d by dx of x cubed. We take the minus sign out, right? D by dx of 3ax plus d by dx of 7, right? Simple, sum rule, right? Okay. Now, the derivative of a constant with respect to a variable is 0. Why? Because, well, there is no variable here, right? So how can you differentiate? You change x in whatever way you want. The value here is going to remain 7 for this particular term. So this term, a constant, has no dependence, right? There's no dependence on x. The term is 0. So that's gone. We're left with 2 terms. Now what we're going to do is we're going to tackle the middle term, right? Next. Now, like I said, there's 3a times x. Now 3a is a constant. So one way to do this is you take the 3a out, because again, it's not dependent on x, right? So actually you can just take the 3a out of the derivative and differentiate x. But why are we able to do that? Right? Well, let's look at the example. So let's take 3a together. You can do it as 3 terms, but 3 and a are both constants. Let's just take 3a. So the product of 3 and a, 3a together. So you've got 2 terms, 3a and x. Now, what does product rule tell us? It tells us that the derivative of a product of 2 functions, when you take f of x times g of x, and you differentiate that with respect to x, then what you can do is say first d by dx of f of x, so differentiate the first term with respect to x, and multiply by the second term, g of x. And then you say, to that you add, you take this first term, now you've already differentiated, so you don't differentiate it again. Take that and multiply that by the derivative of the second term, right? Very simple. So we apply that here. The first term here is 3a, so f of x is 3a, and g of x is x. So what do we get? So this term now is 3x squared. We'll come back to that, right? But focusing on this, you get d by dx of 3a times x plus, now this is f of x, so 3a times d by dx of g of x, right? So d by dx of x, right? Okay. What do we have here? Well, d by dx of 3a is a constant, right? We've already said what happens when you differentiate with respect to a constant. That term goes to 0. So this term actually disappears. Then we are here. Now what do we see here? We have 3a, so that's great. D by dx of x. So you're differentiating something with respect to itself, right? So what happens if you change x by 1? Well, x is going to change by 1, right? So the derivative of a function with respect to itself is 1. So you're left with 3a, right? That makes sense? There's a minus sign outside. Now, let's just come back to this term. I'd written it here anyway. If you remember the rule for a polynomial, the derivative of x to the power of n with respect to x is n times x to the power of n minus 1. So here n is 3, so it becomes 3 times x squared. So what do you have? You have 3x squared minus 3. So hopefully that's really clear, right? We've gone step by step, right? So good. Well, we're going to do another one, right? So let's see how that goes. So f of x is x times sine x, right? We want to find the derivative of that, right? So df by dx is d by dx of x times sine x. It's a product. It's a plain and simple product. So product rule applies. So you say d by dx of the first term times the second term plus first term times d by dx of the second term. So it's d by dx of x times sine x plus x times d by dx of sine x. Now we've just covered this in the previous example, d by dx of x, the derivative of a variable or a function with respect to itself. The answer is 1. And so sine x is all that remains, right? Because you get 1 times sine x, which is sine x. Now here, so plus x, obviously, d by dx of sine x, well, we've just covered, the trigonometric rule or the derivative of a trigonometric function. D by dx of sine x is cosine x. Just go back and take a look at the previous slide, or just keep the lecture notes open, or you can look at Wikipedia as well, another good reference, and you get d by dx of sine x is cos x. So you get this, the derivative of x sine x is sine x plus x cos x. Okay, so that's good. Now let's do something slightly more complicated and also related to deep learning, right? So this is a sigmoid function, right? And as you can see, what it does is it takes the input, which could be any value, right? And it converts it into a value between 0 and 1. So as you can imagine, this is a very good activation function for classification problems. It's also smooth, and it's a good, you know, activation function used quite commonly in classification problems. So let's try differentiating this, right? And see what happens. Because, well, if you're back propagating, you're going to need the derivative. And if you're not, we haven't covered back propagation yet, right? That's, one of the next few lectures. So don't worry if you don't know that yet. So d by dx of sigma x is d by dx of 1 plus 1 by 1 plus e to the power of minus x. Now, what rule do we apply here? We've just covered the first two. The third rule we talked about was the quotient rule, right? This is a fraction, so the quotient rule applies. Well, what's the quotient rule? It says d by dx of f of x by g of x is equal to. Now, this is similar to the numerator. So first thing you do is the denominator, and it's just g of x squared. There's no derivative in the denominator. You just take the denominator of this fraction and say g of x and just square it. So that's the first part sorted. Now the numerator, and if you remember the product rule, or go just look it up again, it's exactly the same, except that now this was a plus there, it's a minus here. So the d by dx of the numerator times g of x, which is the second term, minus f of x, which is the first term, times d by dx of g of x. The difference there was f of x times g of x. Now, because g of x is in the denominator, you have a negative sign here. Right? Okay? Perfect. You can also think of it as d by dx of f of x times g of x to the power of minus 1. Right? That's another example. And in fact, you can go work that out. Just try and see what you get if you use the product rule on that. Okay. So let's apply it here. D by dx of 1 by 1 plus e to the power of minus x. So first of all, the simplest part is keep the denominator and square it. So that's sorted. Now the numerator, right? So d by dx of f of x of the first term, the numerator term of 1 times the denominator minus now this term times the derivative of the denominator. Simple, right? Just go look back, just rewind for a second, look at quotient rule or look at your notes and see if this is correct. Okay, so what do we do now? Let's start simplifying this. So we've got the first term. Now what do we have here? We've got d by dx of 1. 1 is a constant, not dependent on x, right? Again, we've covered this a few times now, or encountered this a few times now. So if you change x, it has no impact on 1. So that term goes to 0, and a product of something with 0 is 0. So this entire term goes away. We're left with just the second term, right? Which is minus 1 times d by dx of 1 plus e to the power of minus x. Now you're already seeing a 1 in this, so you know what comes next, right? So we've got that. I'm just going to write it out for clarity. I take the negative sign out because it's minus 1. Got d by dx of 1 plus d by dx of e to the power of minus x. That's clear, right? It's just this term has gone to 0. And this term now is just been expanded. I've just expanded this derivative, right? You can think of it also as sum rule, right? Where it's just a sum of two terms, and I've just expanded it to split. Now, again, same term, right? So d by dx of 1 is 0. That goes away. We're left with d e to the power of minus x by dx by 1 plus e to the power of minus x squared. Simple. And so just removed all the other terms. Now, we know d by dx of e to the power of x is e to the power of x. Now d by dx of e to the power of minus x, I'm going to give you that value because a good way to derive that is with chain rule. But chain rule is the next session or the next lecture. So d by dx of e to the power of minus x is minus e to the power of minus x. You already have a minus here, so the minus times minus becomes plus, and that cancels, right? Is that clear? So d by dx of e to the power of minus x is minus e to the power of minus x, but you already have a minus sign, right? That comes from here. So that minus and minus becomes plus, and you're left with e to the power of minus x by 1 plus e to the power of minus x square. So the derivative of this sigmoid function is this. Now, if you look at your deep learning notes and look at the activation function, you'll see that the activation function is slightly different. It's actually this, but what you will see is when we do this for deep learning, we now refactor or reformat this a little so that it can be written in terms of sigma. So when you do a deep learning model in your forward pass, you already compute sigma and you can use sigma. So we can redo that, but this is a lecture in differentiation, so we're not going to do that, right? So if you're, don't be surprised if you see, if you look at your notes and or Wikipedia and you see, a derivative of this that is different or looks in terms of sigma, but if you look a little more carefully, you'll see that it actually is this. Okay, so we have already done three examples. We have applied all three rules. We have done derivatives of, you know, trigonometric function. We have looked at an activation function and an exponent. So I think should be fairly clear, right? And in fact, again, encourage you to try out other examples of simple quotient rule, and we'll put a few in the quiz actually on the, with the course notes on the website, right? So pixagon.ai, and so please go there and give it a shot, right? It'll help increase or improve your knowledge or understanding a little more, right? Okay. So it's at pixagon.ai/lecture/derivatives basics review, right? All the lectures are under pixagon.ai/lectures. And the next kind of topic we'll cover related to differentiation is the chain rule of differentiation, right? So that's a very, very key kind of, piece of the puzzle when it comes to backpropagation. And so if you're not familiar with that or just want to refresh, please check that out. Okay. So that's coming next. Thank you so much for listening.